Okay, so as I mentioned, I said we want to look at the applications of dimensional analysis, and I said there are two of them. One is that it can be used to show the correctness of equation. If you know equations in physics, are they correct? We can use dimensional analysis to show that. For example, this I'm going to start from this simple case: v equals to u plus at. Now the hint here to show that equations are correct is that all the dimensions of each term will be the same. The dimension of each term will be the same. For example, we want to show that this equation, let me start from this, I will leave some for you to do. V equals to u plus at. Please, can you stay mute? V equals to u plus at. This is a term. Let me give you one hint here in this box. A term is separated by either plus or minus. But if it is multiplication that is separating two quantities, then we regard them as one. Look at this V is standing alone. I said a term is separated by plus or minus. So if you see A plus, look at now, BC, what is in between them is multiplication. So we take that BC as a single term and A also as a single term. So when plus or minus is separating them, so we regard those as single terms. So V is a single term, U is a single term, AT is a single term. Don't see it as A as separate and then T as separate. So there are three terms here. So what we are going to do using dimensional analysis to show whether they are correct is that we are going to show that the dimension of V is the same as the dimension of U and is the same as the dimension of AT. Is that clear now? So that's what we want to show now. So if all the dimensions of those three terms are the same, then the equation is dimensionally correct. So let's see that now from here now. So what is it? What is V? V is final velocity according to this equation. What is U? U is initial velocity. What is AT? A is acceleration, T is time. But we said we are not going to see them separately. So long as they are joined together as AT, we're going to see them as a single entity, and it must have the same dimension that V and U have. U is velocity. Ignore the fact that it is initial velocity. V is also velocity. Leave the fact that it is final. So final or initial does not matter. What matters is V is velocity, U is velocity. And what is velocity? Velocity by definition is displacement over time. Displacement over time. What is the dimension of displacement? Displacement is in meters. So the dimension is going to be what? When the unit of something is meters, what does that mean? What's the dimension of that? That's the dimension for length. So that is L divided by, this is T. Sorry, this is T. So the dimension for this is going to be T. So we prefer to write this as L T raised to power negative 1. Okay, so this velocity here is L T raised to power negative 1 equals to, what is this initial velocity? It's also velocity. It's going to be also what? L T raised to power negative 1. Then plus, what is AT? Acceleration, if you have looked at dimension very well, acceleration has almost the same dimension as velocity, but instead of having negative 1, it has negative 2. You should have memorized all of them now. So the same dimension as this velocity, and this velocity is this acceleration, but it has minus 2 instead of minus 1. So I'm going to write the dimension for ordinary A, which is L T raised to power minus 2. Then this T here is time. It shows multiplication. Both of them are separated by multiplication. So multiply by, what is T? Dimension for T is what? Capital letter T. Okay, so we are now going to combine these two together. So this is going to be LT raised to power negative 1 equals to LT raised to power negative 1 plus L. This is T to the power 1. This is T to the power negative 2. If you combine, yes, if you combine minus 2 and 1 using indices to combine these two t's together, it's going to be t to the power minus 2 plus 1. We add the powers together. So what is now minus 2 plus 1? Minus 2 plus 1 is minus 1. So this is t to the power minus 1. If I put it here, t to the power minus 1. How do we now know? Is this equation now dimensionally correct? Yes. What matters is this is lt to the power minus 1, lt to the power minus 1, lt to the power minus 1. So the condition is satisfied. So we now say that the equation v equals to u plus at is dimensionally correct. The equation is dimensionally correct. Let's pick another one. The equation that say v squared equals to u squared plus 2as. Let's look at this as well. Equation v squared equals to u squared plus 2as. There are three things here now. Please, ordinary number or constant do not have dimension. In physics, we say they are dimensionless constants. They do not have dimension. So we are not interested in this number 2. The number will appear in front of the dimension of this as, acceleration, and s is distance. Final velocity squared equals to initial velocity squared plus 2 times acceleration times distance. S is distance. Anything distance is length. So it has dimension for length. So what are we going to do here now? We are going to write the dimension of v, which is velocity. What's velocity? Lt to the power minus 1. But this velocity is being squared. So put bracket around everything here and say it is squared. Equals to initial velocity is also u. It is also velocity. So write lt minus 1. Then it has squared. Okay, plus write this number 2. Number does not have dimension. Then what is this a? After a is lt minus 2. I told you that. Then s is distance. Distance is a length. What's the dimension for length? L. So we are going to combine this L and this L. And then see, do not forget indices. This L will carry this power 2. And then this minus 1 that T has here, we also have power minus 2. If you have something like this, A, B, and then there's a power n outside, okay, A is going to be raised to power n, A to the power n, then B is also going to be raised to power n, B raised to power n. Okay, so that's what's going to happen here. So let's do that for these those ones that have squared. So this is going to be L raised to power 2, L to the power 2, T to the power minus 1 times 2 is also going to be what? Minus 2. So L2 t to the power negative 2 equals to this L that has power 1 before will be multiplied by this 2. So it's going to be L to the power 1 times 2, 2. Then t raised to power minus 1. Minus 1 times also 2 is going to be minus 2. Those two are correct. So let's see how it applies here. Plus 2. We shall ignore 2. Don't, because of the fact that this last one has 2, this one does not have 2, this one does not have 2. Now say it is incorrect. No, it is correct. We ignore the 2. Just put the number. We are only going to look for those quantity that have dimension. If we combine this L to the power 1 to this L to the power 1, it's going to be L to the power 1 plus 1. So that is 2 L to the power 2. And then this already has t to the power negative 2, t to the power negative 2. So if we now look at this equation, we see that this is L2 t to the power negative 2, L2 t to the power negative 2, L2 t to the power negative 2. I told you this number does not matter because each and every one of the quantities have the same dimension, L raised to the power 2, t to the power minus 2. Then we say that the equation v squared equals to u squared plus 2as is not just correct but dimensionally correct. V squared equals to u squared plus 2as is what? Dimensionally correct. So the last one that I want to look at, I said I'm going to leave it for you before. Maybe I'll send in chat the one I would like you to do by yourself. This is s equals to ut plus half at squared. You're all familiar with these equations. Okay, so I'm going to attend to that woman later in class. So what is s? S is distance. What is u? Now, how many quantities are here? Do not count it as s, u, t, a, t. No, don't count it. I told you if multiplication is what is combining two quantities, see them as one. So I have s here, that's one quantity. Ut, they are combined. This is under one quantity. Then at squared, that's another one quantity. So I'm going to multiply the dimension for u with the dimension for t and get a single quantity. This half is a number. Yeah, it is dimensionless. It is dimensionless constant. Numbers are constant. So I'll find the dimension for acceleration and multiply it by dimension of time and then put power 2 for the dimension. So let's go. Let me clean all these circles so I don't cause confusion. So this is now dimension for s. S is what? Distance. What is distance? Length. What's the dimension for length? L. Because L is standing alone on the left hand side, this combination two, when I multiply them together and find their dimension, should give L, and these two should also give L. If you now, they are now L equals to L plus whatever number of L, then the equation is dimensionally correct. If only one of them is different, maybe it ends with L squared, there are two things that could have happened. Maybe you made mistake, or the equation is actually dimensionally incorrect. So any equation that is dimensionally incorrect, each of the terms there will be separate. One of them may be different. So let's go now. U is velocity. What kind of velocity is that? Initial, but velocity is L t to the power negative 1. That is just for velocity. Now t is time. What's the dimension for time? Capital letter T. That's coming to combine them plus write this half. There is no dimension for that. What is A? A has almost the same dimension, its acceleration, as velocity, but instead of t to the power minus 1, it is t to the power minus 2. So it is L t to the power minus 2. Now, the dimension for this t, capital letter T, is time. And then t is having square, so I'm going to square it. Remember, while we were dealing with this one up, all the dimensions of v squared that have squared, after finding the dimension of v, we put square outside. So the same thing is happening here. I put square on top of the dimension for time because the equation half squared. So now let's continue. This is L equals to, now the terms that are, when nothing is written, it means it is power 1. So now I'm going to write this is L, then t raised to power, I'm going to add this minus 1 plus 1, because if I have x to the power a multiplied by another x to the power b, I'm going to pick one x and say a plus b from indices. Now the powers here are minus 1 and plus 1, so I'm going to add them together. Minus 1 plus 1, that is that, plus 1 all over 2. I'm going to combine this t to the power minus 2 and t to the power 2. So this is L t to the power. Now I'm just going to add their powers. Minus 2 plus 2. You can also see for yourself that those are going to be 0. Minus 3 plus 3 is 0. Minus 5 plus 5 is 0. So this is L equals to L t. This is going to be t to the power 0. Somebody is moving cursor and thereby writing on my on this place. I think that's Medina. So this is L, then t raised to power 0, because minus 1 plus 1 is 0, plus half L t to the power minus 2 plus 2 is also 0. Now, what is t to the power 0? That is 1. So this is L equals to L. T to the power 0 is 1. 1 times L is L. I don't need to write it. Plus half L t to the power 0 is also 1. I don't need to write it. So because if I change this to 1, 1 times L is L. So I now have L. So my conclusion now is the equation S equals to U squared plus half AT squared is dimensionally correct. V equals to root 2AS. Now, sorry, V squared equals to, I'm getting this equation from this same equation that you know. V squared equals to u squared plus 2as. So it is that I'm not going to put square here again. I've changed it to square root. I've changed that to square root. So is this equation dimensionally correct as it is now? Who can give us hint on what to do here? Is this equation dimensionally correct? Of course. Let's see. What is the dimension for v? The dimension for v is velocity. So lt to the power minus 1. Now there is square root here. So this is going to be 2. Then what is dimension for acceleration? L t raised to power minus 2. Now, what is the dimension for s? S is distance, that is length, L. Okay, now, so what's going to happen here? Let's see. This number, I'm going to separate this number. First of all, under the square root, let me combine these two. So this, sorry, there's equality here, I made mistake. So L t to the power minus 1 equals to, let me separate. Do you know that square root, if you have square root 2 multiplied by another, let me put a l, you can separate the square root, that this is square root of 2 times square root of a times square root of l. You can separate, but I only want to separate 2 to stand alone. This is square root 2 standing alone. Okay, then I'll combine this because they are dimension. Now this l to the power 1 and times L to the power 1. Indices says change it to L to the power 1 plus 1, 2. Now T to the power negative 2. Now, what is going to happen here? If you have square root of a squared number, square root of 2, 2 is now having squared. This square root will cancel this power 2. The answer is going to be 2. So if you want to find, for example, the square root of 89, you know that the square root of 89 is 9, but I want to show you something. Change the 89 to 9 squared. 9 squared. Then this power cancel this, sorry, this root cancel this power. Then you have the answer to be 9. And you know that the square root of 81 is actually 9. So all those things that have power 2, actually it's not just power 2. If the power is even, square root will divide the power into 2. Let me show you something before, so that you know that it's not just about 2. It's about from your indices, this elementary mathematics. If you have square root, for example, square root of x to the power 4, y to the power 6, the answer is going to be square root will divide this 4. What is 4 divided by 2? This square root means 2. It's going to be x to the power 2. Now, this square root also divide this power 6. What is half of 6? It's going to be y to the power 3. That's what it does. So, anything that have 2 before, 2 divided by 2 is going to be 1. That's why we have the square root of x squared. So this square root means 2. So 2 divided by 2 is going to be x to the power 1, and that's just ordinary x. So that adds to your knowledge. So if you have square root of x to the power 50, the answer is going to be, this square root will cancel this 50. We divide the 50, is going to be x to the power 25. Add that to your indices knowledge. So let's continue, and then we'll stop here. I just want to take the one that have square root, and here is it now. So who knows what is going to happen here now? This is going to be lt to the power minus 1. Sorry, I think this should be t to the power minus 2. I have minus 2 here. Yes, I have minus 2 here. So that t is minus actually minus 2. So what's going to happen here now? I'm going to write equals to square root of 2. That's just ordinary number. I'm not interested. Now this square root is going to cancel this 2 for this l. If you like, split it back, split it like this: square root of l squared multiplied by square root of t to the power minus 2. So what is going to happen here now? This is going to be lt to the power minus 1 equals to square root of 2. Now this cancels this. It's just going to be l, which is to the power 1, and then this t minus 2. If you divide it by, sorry, this minus 2 here, if you divide it by 2, what's going to be? It's going to be minus 1, equals to minus 1. So this is t to the power minus 1. So this is lt to the power minus 1 equals to a number. We don't care about number. Lt to the power minus 1, because lt to the power minus 1 equals to lt to the power minus 1. Then the equation v equals to square root 2as is dimensionally correct.